So we're going to be talking about the basic robot systems. So, one of the first things we need to talk about, and I'm going to go ahead and just put all these up here, make it faster and easier. One of the first things we got to talk about is the end-of-arm tooling. Now, why do we call it end-of-arm tool and not, why do you think I didn't say gripper? Hmm? Not all end-of-arm tools are grippers. That's exactly right. End-of-arm tooling. So you've got things like welders, you've got paint sprayers, you've got grippers, of course. You can put pallet lifts on it. You can put anything you want on it. The only limit is your imagination and the job that it's trying to get it done. They even have grippers that can change, or they even have. Try to slow down here. They even have the ability to change out the different styles of the changeover. So let's say you're a windshield factory and you've got to install the system that actually holds your mirror and all that to it. Well, there are different models for different models of cars, right? Not to mention, is it a luxury car versus a regular car, or is it a truck, what have you, right? So the way you give yourself that flexibility is you give the robot the ability to change out the tool. A gripper is a common end-of-arm tool used for grasping, lifting, and moving objects. It's extremely common, that's why most people tend to think that a robot's tool is a gripper, but that's just not the true fact of the matter. Does that make sense? A lot of the time, that gripper is not what you think it is. So the gripper is not always the end-of-arm tool. Sometimes it can be just about anything else. Okay? Sometimes it can be just about anything else. Alright, so we also have what's called a teach pendant. This is a very common programming device. Okay. This is a programming device that moves the robot manually through its motions. You have the controller. This is what actually runs the robot system. So if you're so the difference between a controller and a teach pendant. A teach pendant is what gives it commands. So think about it as a game of Simon Says. If that makes any sense. You're using the teach pendant to say Simon says this, Simon says that. If Simon doesn't say on that teach pendant, the controller will not send the command to the robot. Does that make sense? The controller is the actual, almost physical brain. It's a computer. That is what actually runs the robot and takes feedback from the robot as to what it's trying to do. Volatile memory. This is what anybody's ever had a computer for 5 minutes and lost data because of it knows what volatile memory is, right? It's that thing of if you do not save your work, what happens to it? If the power goes out. All that work goes bye-bye and heads off down the giant trash heap in the motherboard. So that's volatile memory. It's what loses its contents if you don't have power. These robots have two power sources. You have your AC power source and you have a DC power source. The great thing about the the yellow robots, is they run on basic C cell, D cell. Big guy runs on D cell. Little guy I think runs on either C cells or, yeah, I think he runs on C. And what that does is it allows for the robot to maintain a minimum level of power so you don't lose all your memory and have to go back to reteaching everything. The other robots have lithium batteries that need to be replaced in a totally different way. But that is that. Non-volatile memory is what maintains its contents when the power is removed. So that's your basic operating system. So on your computer, if you have a Windows computer, whenever it comes up and does Windows, or Windows 10 or whatever it is, that is your operating system. That is the one thing that will not be dumped, or one of the things that won't be dumped. Otherwise, everything else just kind of goes by the wayside. Another way you can think of it is volatile memory. If you ever turn your phone completely off and turn it back on, all the stuff that does not come up, that was volatile memory. Non-volatile memory is the operating system that allows you to at least make a phone call or a text. So speed. This is the maximum rate of motion for a robot arm. Okay, a lot of these guys are very fast. If you get them going really fast, you'd be surprised just how fast they do go. Yeah. Y'all good with this? Move on. So what is an industrial robot? You have a alphabet agency called the International Standards Organization, and they define a robot as an automatically controlled, reprogrammable, multi-purpose manipulator programmable in 3 or more axes. Now, they're saying that it's specifically this is for an industrial robot. Why do we need to clarify that? Huh? Because there's more than one type of robot? Is that what you're saying? That's true. Because if you think about it, we've called a lot of things robots over the years. If you think back to in the early 2000s, early to mid 2000s, they had all sorts of toys coming out that could walk on their own. You programmed them from a remote, things like that, right? Those were technically robots, but they're not an industrial robot. An industrial robot, this is the exact definition as determined by the International Standards Organization. Now, you have several buzzwords here. One of them is reprogrammable. Why do we want something that's reprogrammable? Be able to use it for a different task. Very much so. Nothing else, you can kind of consider it as so no matter what job you give a robot, sometimes you might have to change its job. If you have to change the job, you got to be able to reprogram it for its new job. That it's multi-purpose. Means that it can do whatever job you ask it to do. As for axes, that's going to be where each joint where the robot moves. Does that make sense? The Robot Industries Association. They define the robot as a reprogrammable multifunction manipulator designed to move material, parts, tools, or specialized devices through variable programmable motions for the performance of a variety of tasks. So, buzzwords coming back, reprogrammable. That seems to be a very big buzzword, right? Reprogrammable means that I can program it once, but then I can come back and reprogram it again. Multifunction, that popped up again. So, yep. Everybody good? Everybody need a minute? Okay. Reprogrammable, it means that it can be a device whose actions are controlled by a stored program that can be changed. So basically, it's a computer, right? Because we can go in and change any document, we can go in and change the operating system, we can do a lot of things with a computer. Because it's what? A computer is reprogrammable, right? Multifunction, more than one task can be completed. That's very true of these guys. If you program them right, you use the right tool, these guys can do just about anything. These robots right here could all do welding if they really wanted to. All we would have to do is change out their current configuration of a gripper into a welding torch or into a sonic welder, ultrasonic welder. Those are kind of cool. So the field of robotics is the study, design, and use of robot systems for manufacturing, and that's from Wikipedia. Robotics have actually been around for a lot longer than people think. And one of the things that nobody ever kind of considers is that how many of you have ever seen a mechanical wind-up toy that actually has the ability to do several things at once? Because one of the cooler ones of those was actually made supposedly by Leonardo da Vinci. And he had made a clockwork lion that you could wind it up and it would walk around and it could roar. And there was certain compartments that it could, show the fleur-de-lis of France, because it went to the King of France. Technically, it's not reprogrammable, but it could be considered a robot, because how different is that from any of the ones we use today? All of it uses gears and clockwork. A very rudimentary program, right? You change up the clockwork bits, you probably could change up the program. So robotics has been around a lot longer than a lot of people think it has been. And it's a very interesting field of study just because it's one that is constantly changing. 10, 15 years ago, that red robot called Sawyer, he was not around really. If you go back about 20 years, nobody really was getting into a robot's workspace. He probably was really under development about then. Most of the time when we think industrial robots, we think our big yellow robot over here. And that is a big yellow robot. That one was donated to us by Mercedes whenever they decided to switch out robot lines. They went from using a what is called a FANUC, which was very popular here, and they went to what is called the KUKA. KUKA was the one that they mainly wanted to use, but they really could not find it over here in the U.S. Or at least not in Alabama. So they originally went with the FANUC. When they decided to change over, they gave away all the old FANUCs, and we got two of them. One of them is operational. That is what we typically work around when we think of industrial robots. The funny thing is, those robots don't get a good rap most of the time because, we won't go into that yet. So manufacturing systems, you have production hardware, you have programs, personnel organized into interactive groups for the purpose of converting raw materials, parts, and information into products and services in the world marketplace. In other words, this is anytime you get a group of people that you take something that is a raw part, let's say wood or metal. Look at what a car is made of. It's made up of aluminum and steel, right? Mostly aluminum these days, more so than steel. Okay, you use robots, you program robots to do a lot of the welding these days. You have to have different ways to assemble it. You end up with a lot of personnel that do come in and help put things together. Okay, what you're doing is taking that raw material and making something out of it. Trying to go ahead and get all the words up here, that way it's so what can an industrial robot do? And here's where I generally tell everybody the same thing I've said all the time. A robot can do anything that you put your mind to making it do. Does that make sense? If I decide to take one of these and make it into a paint sprayer, where all it does is it sits in a booth and it sprays paint on a car body, I can make it do that. I can make it weld. I can make it tend a machine. What does it mean to tend a machine? If you have 10,000-ton presses, you don't want a human getting their fingers in there. That would be bye-bye fingers. So one of the things we do is we can make the robots come in and lift whatever's in there out and get it to move to where it needs to be next. Assembly. Now, a lot of y'all can look at this and it kind of seems a little strange that we use it for so many different things. This is where that myth tends to come in that robots are what? Robots are taking our jobs, right? We've all heard it. We all have heard it, and we've all kind of probably even said it ourselves a couple of times. Robots are taking jobs. Except they're what? They're creating jobs, yes, because they're creating more skilled jobs. A. B, they're taking the jobs humans really do not want. To give you an example, I did work in automation for a little bit. One of the systems that we put together, we had a big robot. It was a moto man, essentially. And the whole point of this moto man was to lift pool heaters. Have y'all ever seen what the size of a pool heater is? They're massive, right? They stand about yay tall and they weigh a lot. So this robot, what it was supposed to do is what's called palletizing, where a pool heater would come down the conveyor belt, the robot would come in with its forklift attachment and pick it up, it would set it on the pallet, and then it would wrap it in shrink wrap before it would pick it up and send it out the door. Now let me ask you as the humans, what impact would that have had on a human body? Because we aren't talking something that weighs 10 pounds. We're talking something that weighed in the excess of 100 pounds or more. So first of all, how many people would it take to lift something like that? Minimum of 2 people, if not 3 or 4, right? There's only so much strain you can put on the human body. How many of you ever remember the mantra of lift with your knees, not your back? How many of you know what that even means? I've got 2 people that know what that means. Anybody else? 3? Y'all don't? What it means is that whenever you're lifting something, you're supposed to face it square on, squat, pick it up with your knees, not your back. Why? Because your back is one of the most vulnerable parts of your body. It takes nothing to slip a disc, strain your back, and 1,001 other things. And we won't even talk about the fact that you can overcompress or blow out a disc in your back or even break a vertebra if you put too much strain on your body. So these giant pool heaters have to be palletized somehow. You think they want to hire a bunch of people just to stand around and do that? Or would they rather, especially when you consider the fact that eventually somebody's going to get hurt. You know, it's very easy for a human to have things slip through our hands. You know, you get tired, your hands get sweaty, you don't have the strength you had whenever you started your shift at the end of your shift. So chances are, fingers can get broken, feet can be broken, all sorts of things, right? So it's not a real safe job for humans. And then you also have the fact that after that happens with an accident, what do you have to do? You have workman's comp that you have to shell out money for. So whenever they sit there and say robots are taking the job, yeah, they kind of are. Because yes, you can hire people to do that. Yes, you can have people that stand around all day long taking these pool heaters, putting them on pallets for shipping. So yes, they did take the job. But it's a job nobody wants. Right? It's a job that nobody wants. And in the process, not only did they take the job, they created a job. Because now somebody has to keep and maintain the program as well as maintain the conveyor belt. Anytime somebody comes up to me and tells me that robots take jobs, that's exactly what I tell them. I say, hey, look, yeah, they take jobs. They also create jobs, and they take the jobs we don't want. They take the jobs that HR finds a nightmare to actually implement, right? Everybody knows what I'm talking about when I say HR? Yep. People that sit there and put out ads all the time going, please come work for us. Please, we're desperate. Come work for us. Every time you look in the newspaper or you see ads on TV. They're the people that you have to talk to get people hired in. But they're also the ones that have to let people go or, you know, sign the check for somebody to get workman's comp. So yes, they take jobs. They also create jobs, and they also take ones we don't want or that can't be really filled easily. Inspection. How can we set a robot to do inspection? What do y'all think? You can have gauges. What else? Pictures. You can mount cameras to these guys, and they can actually move themselves around something. One of the ones that I've seen do that is I've seen a robot that can inspect an engine, a car engine. Think about that for a second. It's not that we don't want that job. It's just that sometimes we miss clues that say, hey, yeah, that's got to go back to production. There's missing something right here. Whereas the robot's going, okay, that tab's there, that tab's there, that tab's there, that tab's there. Okay, so inspection good, on down the line. Or it can sit there and go, oh, that tab's missing. Okay, hey, person, come get this thing and go take it back where it goes. It's not ready to go down the line yet. So they're a little more accurate than we are. Goes back to that we're human, right? Cleaning. If you've ever had a Roomba or one of those little floor robots, they do a great job at that. They can also do other forms of cleaning. Heck, you could stick a pressure washer on those things. As long as you protect the electronic circuits from it. Glue. That's interesting, right? Glue. Gluing and gaskets are probably the two most precise things that robots are very easily capable of doing. Y'all know what I mean? Think about it. If you have to put a very precise bead of glue, or you're trying to create a silicone gasket, how steady is your hand whenever you're trying to do that? It's one of those things that if I was to take a marker and try to draw a single straight line, what do we have a problem with? Is that a single straight line, or does it start to kind of wave and curve? That's kind of the problem with humans. A robot can do that straight line, eyes, no problem. That's why gaskets are so much better these days. That's why engine efficiency is so much better these days. You have robots that actually apply the gasket in factory and into a very precise, specific configuration. That means that the gasket, whenever it's created by the smush of two parts coming together, that gasket's not going anywhere. You don't have leaks, you don't have drips, you don't have things going completely off path. That's why they're great for glue and they're great for gasketing. Milling, drilling, testing, cutting, grinding, it goes on and on. One of the more common ones is a gripper. Why? Because material handling, machine tending, assembly, pick and place, packing, palletizing, gluing, cleaning, a lot of things can be used with a gripper. Why? Because a gripper works almost like your hand. Anything you can make your hand do, you can make the gripper do, right? Depending upon the configuration. But the good thing about robots is that instead of having a vulnerable hand, is that we can change it out to something like a welder that is permanently attached. An industrial robot will do its program task with high endurance, with speed, repeatability, and precision. That is the good thing about a robot, is that they are very precise. One of the best things about a robot is its precision. If I was to take a pin and just raise and lower my arm, would I come down on the same dot every time? Would a robot? That's the good thing about them. They've got great repeatability. They've got high endurance. These guys don't need a break every, 2-3 hours? Maybe 4? These guys don't need that. They run 24/7, 365, and it does not bother them. What you have to make sure you do, though, is what? Sometimes you have to go in and do maintenance on them. Because eventually things do start to wear out. Okay. So here's a basic system. You have the robot controller, which is, again, essentially nothing but the robot's brain. And that controller talks to the teach pendant. It talks to the data storage devices, things like a USB stick or something like that. It then talks to the robot arm. The robot arm itself is talking to the controller, the tool, and the power source is coming into it. These guys don't run 120. I believe most of them run higher, like 3-phase power. Not anything you want to get across. So, additional devices here. You have the tooling, you have the teaching device, data storage. Now, these guys don't come with data storage. They have a way to access data storage, just like your computer. How do we access data storage on our computer? Hard drive. USB. You have, those of us who are older remember the floppy disk. And its cousin, the giant floppy disk. CDs, DVDs. That's data storage. Good way to save a program that you need to take to another robot or something. Okay. So we try and use these guys to emulate the human arm, which is kind of funny because we don't really think much about our human arm, do we? For instance, how many joints do we have in the human arm? We have 3. Wrist, elbow, shoulder. Okay? How many movements can your shoulder do? It has the ability to rotate and thus move your arm into any position. But it has another ability. That's that it can come up and down. Okay? So it has 2 different functions that it can mainly do. The robot has to have both functions separated. So it swivels around the base and it swivels at the shoulder joint. How many functions can your elbow do? What? Now you can just have one, right? The elbow is there are 2 joints that are extremely vulnerable on the human body because they only work one direction. And that is your elbow and your knees. All right? Because if you bend your elbow past this point, you're going to end up breaking it. Robot's a little more flexible in its elbow, but we have a different range of motion than it does. It takes a lot more for it to do the same thing. What about our wrist? Now here's the funny thing. Your wrist can roll just a little bit, moves up and down, and moves left to right. Your wrist has a bunch of little bones that do that. And in order to do that with that arm, you have to have 3 axes. All right, so it provides specific motions that will enable the tooling to do the work. Let me put that in perspective, a different perspective, if you will. What is the purpose of one of these, besides to be a giant paperweight? Why do we want a robot? We use it to perform tasks, right? We use it to perform work. The whole purpose of the robot revolves around the tool. Does that make sense? It quite literally revolves around that tool. Most robots, well, I won't even say most, I'd say more like 90% of robots tend to be run by electricity. Some are run by hydraulics or pneumatics, but 90% of it is all run by electricity of some sort. And there's 2 ways that they move. They either move in a straight line or they rotate. And the ones we tend to work with right here are all rotational axes. This kind of shows you what I was talking about earlier. You have that first rotation around that base. You have the second part of the shoulder that moves it up and back. You have your elbow. Then you have your 3 wrist movements. Okay. A controller, this is what monitors and affects the operational conditions of a given robot. Okay, it is a computer. I've said that several times. It is a computer. One of the things people tend to think about when they think robots is they think that it's something that is intelligent. Do these things actually have any real intelligence? No, they don't. Can we make it seem like they're intelligent? Oh yeah, we can make it seem like they're intelligent. But at the very depths of it, it's nothing but, if you got rid of the controller, these things are nothing but a giant paperweight. Okay? And even with the controllers, if you do not put commands into the robot, again, it's nothing but a giant paperweight. That computer is what controls everything. It allows users to create, copy, edit, and select programs. It controls the position and speed of all the joints, holds the configuration of the robot, and has several ports on it that give inputs and outputs. Why do we need ports for inputs and outputs? Okay, so what do you mean by that? Communicate with the outside world. What do we generally hook up to one of these guys? An HMI or a PLC, programmable logic controller. We hook those to them very frequently because we're using sensors, we're using all sorts of other devices along with the robots. So we typically will hook them all together through either a PLC inside the robot or an external PLC that says, okay, this command has been put through, so go to the next command. This is checked off, go to the next thing, right? It's all still a game of Simon Says. Here's my task that I want you to do. Here's the instructions on how to do it. Go forth and do it. Okay? And you've got your teach pendant. Basically, this is your controller interface. So basically, the controller is the bottom portion of your laptop. This is the screen where you actually tell it and input things to do. Does that make sense? You have your base of the laptop. You have, even better, you have your tower. That is exactly what the controller is. If you look at a desktop version of all this, it's a tower. What interacts with the tower? You have the monitor and you have the keyboard, and maybe even a mouse. So anything you would do to interact with that tower would be done through the monitor, the keyboard, and the mouse. So that way you can create, name, edit and copy programs, work on the robot system. Mode of operation, there's generally 2 or 3 modes of operation. There's either the operator, in other words, somebody programming it, and then you have like the administrator that is able to go in and do things like set passwords or mess with the configuration of the robot. You have security levels that tend to go with that mode of operation. You have speed, display faults, and what's called jogging, which is something y'all will be doing on Wednesday when y'all get to lab. This is the MotoMan Teach pendant. And that's the FANUC. Now, real quick, what do you have to do to really kind of enable it? What kind of a switch do these guys have to keep people safe when they're in the robot space? It's got a dead man switch. How many of you know what a dead man switch is? Got a couple? So a dead man switch is exactly what it kind of sounds like. It's trying to, we've got a switch that in order to enable a robot, it's a 3-position switch because initially, for some reason, programmers thought that when you get scared, you tend to let things go. Right? You think that if that big robot was swinging at you, that you would just let things go, drop the teacher in it, whatever. Right? What actually happens when you get scared? That fight or flight response kicks in. That does not mean that you're going to let things go. It means you're going to do what? You're going to go, tense up, right? You're going to get really tense. Your hands are going to clamp down on that controller. So that's why you have a 3-position dead man switch. The way you've got to hold these is you have to have the release position, you have the middle position, and then you have the clenched position. In order to program a robot, you have to keep it in that middle position. You can't do the other two or else it sends off an emergency stop signal. Does that make sense? And again, the whole reason they did that was because if you get in the cage with one of these guys, and most of the time, I'll say that because things are changing these days. Things are changing because we now have what are called cobots or cohabitant robots that are very safe to work around. They still need to have their own little bit of space, but if a human happens to get in the way of that robot, anytime it feels feedback from its motors, it sits there and goes, okay, there's something there, I can't move. Okay, so that means I need to stop, and there's something there. So it does not hurt itself. It cannot hurt a human that's around it. These are becoming quite pervasive. These are starting to come into the market. Robots like our big Fanic and these little guys right here, they're a totally different animal. These particular robots, we put them behind cages. We put them behind some form of a physical safety barrier. Why? Give you a really good reason. Big yellow hits you there. You're not coming back. At the very least, it could throw you probably at least halfway across the room. Because I know for a fact that thing can pick up my weight. I'm not a small person. And it does it with total ease. That thing weighs about a couple tons, at least half a ton. Probably about, the tool alone probably weighs about 500 pounds. Maybe a little bit less. That thing hits you, you ain't going to be standing there. So most of the time, these robots are behind a lot of barriers. But if you're the person that has to program it, and you have to go and actually get in the area of the robot, let's say you're doing a weld, and you have to be very precise with that weld. You have to go in and look for that weld right there. Can I do that from halfway across the room? Or do I have to get really up close and personal with that robot? Right? So if I have to get really up close and personal with that robot, I want some way to stop him if he starts moving. I don't want to be crushed. I do not want to be hit. So that's why you have a 3-position dead man switch on every robot teeth pendant. Because if you do get in the cage with a beast like that, you want to be able to make sure it does not swing around and get you. Now, what's kind of good about the robots is generally we don't have to get in the cage with these guys. We don't want to. We program them, we let it run. But the bad thing about these robots is, like Big Yellow is sitting here in this perched position, right? Most of the time, if you see that on a floor, on a factory floor, that robot is not just sitting there. It's waiting. What is it waiting for? It's waiting for a signal to trip it and tell it go. And once that thing starts moving, it moves very quickly. Okay? A lot of people have been hurt because these things, they trip off, let's say, a sensor on the conveyor belt. Right? You have a sensor on the conveyor belt and you trip it just by running your hand along it. That robot's going to jump into action going, oh, my part's here. I need to go do my job. Does it know you're there? Does it realize the part isn't there? No. It's a machine. It's a computer. It knows what you told it. It's saying, Simon said do this. Simon said do this. I've got to go do my job. That's where people generally get hurt. Because they did not realize that robot was just waiting for that signal. When it does, it takes off, and accidents do happen. You got your FANUC teach pendant. By the way, you should notice that each of these have a little red button. What is that? That's your e-stop. Now, I will say this. Before you leave each day after you play with the robot, you need to make sure your e-stop is pushed in. Now, what that prevents is from some random person just wandering in here, picking that teach pendant up and starting playing with the robot. Okay? All right, guys, I'm going to give y'all another 10-minute break because I think some of y'all are falling asleep on me. So input, output. So how we give these guys almost a way to seem like they're alive or intelligent is through what? Through sensors. What do the sensors do? They give feedback from what? They get feedback from the real world, from something that is in existence, right? It has to have some form of mass, air, water, or air, fluid, or solid. Solid, liquid, gas. It has to give some form of feedback at some point. So we do that with sensors on the robot. We do it with sensors on the production line. We even give production equipment a way to feed back to the robot sometimes. And that's how we try and work with this. So they didn't have class in there. I'll take y'all in there and show you what I mean. But every bit of the production system generally has at least one sensor and is trying to give feedback to everything else there. That's why we tend to hook everything up to PLCs. Why? Because PLCs have the ability to kind of control the way everything's running. All right? So this is the inside of the controllers. This particular one is the ABB. That's this guy right here. And what does it look like? It looks like exactly what it is, right? That's a computer. A very big, very expensive computer. By the way, when I was working in automation, at one point we had a leak in the ceiling, and we had a little robot that was attached to our floor robot. And so in order to keep the robot controller from getting wet, what did I need to do? You have to protect it with plastic wrap. You protect the robot with plastic wrap. All to keep everything, water from places it shouldn't be. Just like if you spill water onto a keyboard, what would happen to your computer? It's toast, right? All right, this one's the FANUC. Now, one of the things you should see on each of these, can't really see it very well right here, but you can kind of see it better with a FANUC, is it has a couple different modes. One is called teach mode. All right, teach mode slows the robot down to where it cannot run full speed. Why? Because if we're in the cage with the robot, do we really want it running full speed? Right at us? No. So this slows it down to a couple different ways. This guy has two modes of teaching. He has the basic teaching and he has full speed teaching. I generally keep him on the 250 millimeters per second. And then he has what's called auto mode. Auto mode is where he's going to run the program on production. Does that make sense? In other words, all you do once you put it in auto mode is tell it to go, and it goes and does the job. And it's not going to stop for a while. There's the KUKA controller, the Motomans. We've already kind of gone over this, but yeah, the controller and the PLCs all kind of like to talk to each other. You know, it's always, if you've ever done PLCs or motor controls with relays, you have a series of what? Is this done? Check, let's move to the next. This done, check, move to the next. This done, nope, still waiting on that. Everything pause for a minute, let it get caught up, right? So we have the input-output section, as well as everything else to move to it. And I don't know a single thing that uses a cassette tape anymore. I don't think they even make cassette tapes anymore. Do they? I know they don't make them to play anymore. Used to be the big way you heard music was you had a cassette tape. I don't think they even exist anymore. So power sources. So getting into power sources. Power sources are how everything runs, right? It's how your car runs. It's how anything moves, does anything. We have three, and the first one is, of course, electric. Now, electricity is not that hard to come by, right? We basically can't run a society today without it. Would y'all agree? So, it is the primary power source. Most, if not all, robots tend to run on some form of electricity. Why? Because it's reliable, and I won't say it's 100% safe, but it is the main thing we use. The other sources are hydraulic and pneumatic, and most of the time those are not going to be found on the actual robot itself, but in the tool. As you can see, all of our robots right here all run pneumatics. All of them run air pressure to their grippers. These particular ones all have grippers. So all of them run pneumatics to the gripper. Why would you use hydraulics? Well, not so much just for a gripper, but why would you use hydraulics at all? Why do we use hydraulics instead of pneumatics? Heavier lifting. Hydraulics are a workhorse. I mean, you can do a lot with a very small things, right? So if I take a 1-inch diameter piston for a hydraulics and 1-inch diameter piston for pneumatics, which one can do more work? Your hydraulics do more work. Why? Because hydraulics are not compressible. So the end of arm tooling, or end effector. All right, this is attached to the flange to interact with the environment. The nature of it is only limited by what you're actually asking the robot to do. Does that make sense? That's the only limitation, is what are you asking the robot to do? And one of the things that is, like I said, it's the most commonly weird thing, is that you have a gripper is the fact that the gripper is a type of end of arm tool. It's an extremely common type of end of arm tool, but it is not the only end of arm tool, and not everything is a gripper. And that's something that most people can't ever seem to remember. The gripper is a type of end of arm tool, but the end of arm tool is not always a gripper. Okay? And the grippers themselves come in many shapes, forms, and fashions. Why? Because it all depends on what you're trying to move. So let's say you're trying to move a giant bag of dog food. Is something like this going to work? No. What you might do instead, and I've seen these, is they have these metal fingers that come out. They come down over top, and they come in under the food. It's still a gripper because it is gripping the food, right? But in a way to spread it out and keep the weight from becoming unbalanced, they've got the gripper spread out into several metal pieces instead of one. That one right there is what I'm talking about. All right. You also have deburring, you have drilling, you have spray paint, paint sprayer. This guy's a gripper himself, because what is he doing? He's gripping something. Same for this guy. This one's a suction cup gripper. Pushes those suction cups, creates a vacuum, and picks up stuff that's flat. So you're talking things like those large sheets of paper they'll sometimes stick between different sections of a pallet. Things like that. Or even a very thin sheet of metal. Always depends on what you're working with. And of course, you got a welder. All right, so teaching devices. These are used to program the robot's motions. You have computer simulations. And there's actually a class that we teach called Computer Sim. It permits program development and editing while displaying the system operation of the screen. This is what's called offline programming. There's two types of programming. You have online and offline. Online is not through the internet. I'll repeat that again for those of you that are asleep in my class. Online is not through the internet. Online means you're programming through the teach pendant. Offline means you're programming through the computer. And again, you're not doing it through the internet, you're doing it through a program on the computer. So the teach pendant permits the programmer to move the arm through paths and positions during the programming process. So data storage, you have non-volatile memory and external permanent storage. Why? Because it is very easy to lose your programs, and just like any time you work with your computer, what do? Back it up, back it up. Always make sure you back it up, because why? All it takes is the power to blink and you've lost 3 hours worth of work. Anybody ever have that happen? Especially back whenever things used to be a lot worse with computers. It took nothing for them to black out on you. And all of a sudden you've just lost 5 hours of work and you're just going, oh no. It just gone. Cassette tapes, I don't think are around much anymore, kind of like floppy disks. All of those have kind of gone the way of the dinosaur. Hard disks are still around, I think. CD-ROMs and DVDs are still around somewhere. PC cards, compact flash cards, and thumb drives. Which one of these is probably the most commonly used nowadays? Thumb drive. Compact flash cards are still used every now and then, and PC cards, but thumb drives have kind of taken over the world. What's really funny is I remember when those first started coming out, and they were really, really expensive for like a 500 gigabyte. You paid 20 bucks for a 500 gigabyte. Now you pay 20 bucks for a 10. I'm sorry, not gigabyte, megabyte. And now you pay the same price for a 10 gigabyte. 20 bucks. That's just weird, isn't it? So degrees of freedom. This is referring to each joint or axis motion in the arm. Okay? So we have two different types of axes. And think about it like your arm. We have two different types of axes to move our hand and our wrist to where we need it to be. We have the positional axes. What three are those? Which two joints of ours are those? How do we move our hand and our arm? Let's say if I wanted to reach out and grab a marker. Which are going to do the main moving? Huh? Your shoulder and your elbow, right? If I'm reaching out to grab this, my whole arm's got to move and orientate itself so that I can grab the marker. Those mean they're positional axes. Your arm is moving the position into position to do what it needs to do, right? Does that make sense? Okay? You have the positional axes that move your arm into position. Then you have the orientational axes. These are how you're going to pick it up once your arm gets it there. So move my arm up, and let's say I want to grab it around the middle. I have to turn my wrist, come down, and move my hand in several positions to pick up everything in the right orientation. Does that make sense? So you have the positional axes. Those are your shoulder and elbow joints. Then you have your orientation. That's all in the wrist. Make sense? All right. So I'm not even going to call it the work envelope because work envelope is not really used very much. We're going to call it the workspace. So all points that represent the maximum and minimum reach of the tool in all directions is the workspace. How many of you like to do like a puzzle? Many of y'all like to play with puzzles at all? Or let's say just writing notes. What is your workspace for writing notes? How do you know what you can reach if you're having to write notes down? Okay, that is your workspace. If I'm sitting here, my workspace is everywhere within my hand reach, right? Anywhere I can put my hand, that's my workspace. Same thing for these guys. The workspace is where can it reach to do the job it needs to do. And anything that you want it to do, you may need to make sure that equipment is in its space, right? So can I use my robot to load and unload a conveyor belt if my robot is here and my conveyor belt is over there? No. What I need to do, if my robot is standing here and its workspace includes this whole area right here, I need to put the work pieces right here. Why? Because otherwise he can't reach. Otherwise he's nothing but a fancy paperweight. And that's essentially all these guys are giant paperweights. The only reason we have them is to do the work we ask them to do. And in order to do that, we need to consider where they can get to and how to get to it. Okay? So it is the maximum and minimum reach. So not only can it reach all the way out here, it also can reach right in here, just like we can. Right? So think about sitting at the dinner table. Do you put your glass of water right in front of you, or do you typically sit right here, just within arm's reach, but not with it where you can sit there and go, put water all over your table, right? But where you put the main thing you're focused on, you put your food right in front of you at your minimum reach, so you can quickly put your fork to your mouth, right? Am I going to put my food all the way out here where I've got to reach and drag stuff across the table? No. So that is the workspace. One of the things we got to talk about with the end of arm tool is what is called the tool center point. And I will actually be showing you on the Moto Man how to set one of those up. This is the point on the tool or in space that performs the work for which the robot was purchased to position. And it must be positioned exactly in order for the tooling to perform the job successfully. So let's say a welder. When you first buy the robot, this right here is the end where the tool center point is. But my welder is all the way out here. Where do I want that end of arm tool? Do I want it here or do I want it out here? What y'all think? I want it out here, right? I want it at the end of my welder so that it actually goes and does what it needs to do. How many of you have ever done anything with spray paint? All right. So how does spray paint work best? Up close and personal or held at a distance? You hold it at a distance, it gets a lot more coverage in a lot better way, right? So the tool center point, even if my paint sprayer is here, maybe my spray distance is optimized here. So what I would do is move it from here to out here so that I have that optimized spray distance. Does that make sense to everybody? So it does not have to be on the end of arm tool. It can be located just a little bit out. All right. Trying to keep an eye on time so I don't keep you all over. Robot classifications, they are really generally classed by their work envelope first. The ones we typically use are the spherical polar or the articulated slow down. Articulated, revolute, jointed, or anthropomorphic. Basically means it can get to a varied workspace. How about that? Because I can actually take a lot of these guys and just about flip them over the other side and do work behind them as well as I can do work in front of them. I can also swing it around to do the same kind of thing. Cylindrical, those typically work in straight cylinders. Then you have Cartesian. I think they meant to put rectangular because I'm not sure what rectilinear is supposed to truly mean. Huh? Rectilinear is right? Okay. But essentially all Cartesian is working in a rectangle. Right? I'm having problems with words today. That's all, folks. Rectangular workspace. Okay. So you have this guy right here, number 1. He's our rectangular workspace because he can move left to right, he can move up and down, and he can move in and out. but that is all he can move. So what his workspace is going to look like is basically a box. Then you have this guy, he's our cylindrical, because he can sweep his arm over around, and he can move up and down and in and out, but he cannot move over himself. And he cannot move side to side. He can rotate side to side, but he cannot move side to side. Does that make sense? So his is a cylinder. This guy right here is our spherical or polar, because he can sweep side to side. He can move over himself just a little bit, but not all the way. And he moves in and out. And then this guy is pretty much what these guys are. They sweep around the base, they sweep up and down, they sweep at this joint as well, and that allows him to have just almost 360 degrees of freedom at each joint. Now, do we actually give them the full freedom of 360 degrees? Nah. Why? Because it can mess up the motors, it can mess up a lot of things, and we don't do that. It's not good for the robot. Okay? And by the way, this guy right here, what they're showing you inside the picture, is very close to what the very first robots used to be. The very first robots ever created were what were called unimates. And essentially, this is exactly what they could do. They could move they could sweep left and right, they could move the base up and down, and they could move this little arm in and out. But he did not have a lot of versatility, because he could not move past a certain point in every point. Does that make sense? All right. So you have other classifications of a fixed sequence. Now these would be where you have, if you're doing a pick and place, this is something that you're not going to generally change a lot. So if you are a bakery that makes donuts, a fixed sequence would be something like you just put that on your glazed line, where all it does is pick up the glazed donuts and move them into a box. And that's all it does all day long. Pick one up, move it over. Pick it up, move it over. You're not changing anything about it. A variable sequence, let's say same kind of concept. You have donuts. But instead of it all being the glazed line, maybe you got the jelly donuts there too. So it's got to be able to move the jelly donuts to one box, the glazed donuts or the iced donuts to another box, right? You have a playback. All right, these typically are robots much like our Sawyer over there, where you can literally push him through motions, and he doesn't actually record them, but there are robots that do, that as you push them through motions of how you want it to do the job you want it to do, it records it just like a tape recorder records your voice. Anybody remember those old things? Numerically controlled, that's kind of what these guys are. We classify them on intelligence, which we've already said several times today. Intelligence is not true intelligence, I guess I should say. We can make it seem intelligent because we give it sensors and say, go forth and do. But we do not give it the ability to make actual decisions for itself. Does that make sense? And then we have open loop and closed loop. Open loop is what a lot of machinery is. It means that there is no feedback given either in positional data or orientational data. Nothing gives feedback. And then you have closed loop, that is exactly what these guys are. They give feedback to everything. Okay? They give full feedback. All right.